Another stress transformation problem where we will rotate to a defined angle, and we would do this later in the course with pressure vessels in terms of weld lines. Right here it's going to be a wood member, and we're asked for information along the grain lines. So you can read that. The picture of the stress block is over here on the left. The grain, the wood grain, is at 15 degrees as shown in the picture. And so over here on the right side, we have the axes that we're going to rotate to. So we're going to rotate 15 degrees clockwise. So let's kind of do a little setup here. If we looked at the tensor, and this is a 2x2 problem, or a two-dimensional problem, and so we would have minus 3 megapascals, we'd have plus 2 megapascals. And this is principal. There's no shear stresses on the picture, so we'd end up with 0 and 0. So if we were going to use the equations, right, we could use the Q matrix as seen on your equation sheet. We'll show that in just a second. If we were going to use the other equations, it would be sigma xx is equal to minus 3 because it's in compression. Sigma yy is equal to plus 2. Tau xy, or sigma xy, would equal 0. And the all-important theta, remember we're going to define our angles through a right-hand rule, or if you want to just look at the slope, right, that is created in the direction of rotation. So here we have a new x prime axis that would have a negative slope, so this is going to be minus 15 degrees. So go ahead and take a look down here. All right, we could use the transformation if we wanted to with the matrices. All right, we'd be highlighting that matrix right there by the 2x2 status. If we went ahead and just used the equations, we would end up using these 3 equations. And we have all the unknowns that we would use above. Right, again, remembering that theta is equal to minus 15 degrees. So if you did that, you would find that sigma xx prime would be minus 2.67 megapascals. Sigma yy prime would equal 1.67 megapascals. And we would now have a shear stress, and that would be equal to minus 1.25 megapascals. Remember our stress invariant, so we can at all times add together the normal stresses. You add those two numbers together, you get -1. Back here before we transformed as well, when you added those together, you got -1. So the stress invariant holds. And so this is what we've now done, is we now will draw a rotated stress state, and this is at 15 degrees. Maybe we could label it right there as 15 degrees. Right, remember, this is now the x prime axis. So I'm going to put a big compression, and that's going to be 2.67 megapascals. In the y prime direction, we've got tension of 1.67. And we have a shear stress, right? Sigma x prime y prime is a negative value, so I'm going to go on the positive x prime face, and I'm going to draw a shear stress in the negative y prime direction, and I'm going to call it 1.25. And if I can draw one, I can draw all of them. Remember, our grain is working in this direction. So if you're asked for something perpendicular to the grain, right, it would be sitting right here. And then there would be our shear stress parallel to the grain. So that would be the equation, the equation solution. So solution by Morse circle, we'll present that now. And here's our initial stress state. I'm going to rotate as seen. We've got the grain lines on there. So just to help myself out, I'm going to go ahead and draw the Morse circle canvas. So sigma on the horizontal, tau with clockwise positive on the vertical. And we'll put a scale down here, and that'll be 1, 2, 3. So let's go back up, and remembering really the most important part here is to get our first 2 points. Once we get those, we really can analyze quite quickly anything going on with the circle with sort of simple trig. So on the X face we have -3, we have 0 shear. On the Y face we have +2, 0. So this will fall out quickly here. There would be the X point, there would be the Y point. So I can connect those two, and this is one where you don't need to memorize a formula too much. We just need the middle of that line. You can see clearly it's going to be there at about -0.5. So we can go ahead and call the center, which is equal to -3 + 2 divided by 2, right? That's just sigma average. And we would need a radius then. So we would be going from -3 to -0.5. So we get a nice R is equal to 2.5. So what we're looking to do in this problem is rotate 15 degrees clockwise. And that would mean on Moore's circle, remember everything on Moore's circle is twice what it is in real life. So we would be rotating 30 degrees clockwise. So we'd be looking for the answer right there. There would be X prime. There would be Y prime. And so what we need are the coordinates of those 2 points. Right? That's what we're looking for. So I'm going to get a new color here, and let's just kind of highlight that triangle. And this is going to be 2.5. I'm going to call this side down here L1. I'll call that L2. So we'll just have some simple trig to find some lengths here. So L1 would be equal to R times cosine 30 degrees, which would equal 2.17. L2 would equal R sine 30 degrees. That would be equal to 1.25. So that would tell me the coordinates of X prime. The coordinates in the horizontal direction, it's -0.5, which is the middle of the circle, minus 2.17. And that'll get us all the way to that point right there. And we're going to go up 1.25. So let's see what that turns out to be then. -2.67 comma plus 1.25. So we've done the same thing over here with Y prime. Right, so this is the exact same triangle right there of 30 degrees. Therefore, that would be L1. So that would mean that Y prime would be at -0.5 plus L1. So plus 2.17 comma minus 1.25. So the coordinates of Y prime would be 1.67 comma minus 1.25. So let's go ahead and draw the rotated stress block. I'll go back to black. That is rotated. I know we did it at 30 degrees on Moore's circle, but it is 15 degrees in real life. And so there's X prime. There would be Y prime. So on the X prime face, I'm just going to plot these. I'm going to plot the coordinates. I'm going to plot the stresses. So I get compression, 2.67 from the negative. All right, now remember the sign convention. I get a positive shear stress, which would mean that in Moore's circle land, that means that on the X prime face, my shear stress would be causing clockwise rotation. So that shear stress right there would cause clockwise rotation of the X prime face. If I can draw one, I can draw all. Let's go ahead and look at on the Y prime face, we would have in tension 1.67. And we can go ahead and check our shear stress. We have a negative, which would mean we would draw it causing a counterclockwise rotation, which is what we already have. So there would be the exact same answer by Mohr's circle.